All right. I'm just going to record myself going through this page and talking about it. I think functional programming is pretty cool. And, the jargon is not the interesting part, but it's kind of like a good check to see if you understand the concepts. All of these pieces of jargon should already have little places in your mind. And you can just bring up that whole like chunk of meaning from the single word. So, yeah. It's kind of cool. They have all these functional programming concepts like shown using JavaScript. You can use any language, but I guess JavaScript is just a really common one. Here's the table of contents. We'll scroll through that real quick and get started. Arity. By the way, I'm just going to read every single one. This is mostly for me. You'd be quicker to read it all by yourself, but maybe you'd get bored. I don't know. This is like a read along or like whatever. So anyway, arity. The number of arguments that a function takes comes from these words. This is definitely a really weird one. Nullary. It's like that word only makes sense when you're using it in the context of binary and unary. I don't think that anyone would say this in and of itself unless they're like, oh, this is a unit function. Unit being the type that only has one possibility. Boolean being a type that has like two possibilities. Int being a type that has 2 to the 32, 2 to the 64, whatever possibilities. Higher order function. Function which takes a function as an argument and or returns a function. Um, it's like there doesn't really need to be a special word for this because the differentiation between functions that are purely values and functions that are functions themselves makes a little bit less sense if you think of functions as the exponential type, compared to the product type, like a struct, or the sum type, like a discriminated union. But we're humans, and so we like to make distinctions, like the difference between a process and a thread, the difference between a function and a higher order function. From one perspective, they're totally valid and like a huge difference, and it requires a different style of thinking. But from another perspective, they're identical. Closure. A closure is a scope which captures local variables of a function for access even after execution has moved out of the block which it is defined. This allows the values in the closure to be accessed by returned functions. So you're kind of like closing, uh, like you're closing a bag of scope and capturing something else. So let's check this out. Um, wow, I guess I wouldn't call this a closure, but rather a curried function. But that's all right. In this case, X is retained in add to five's closure. Yeah, okay. So it's my definition of closure that's slightly wrong, not theirs, with the value 5. Add to 5 can then be called with Y to get back the sum. When I think of closure, I think of like setting a variable and then defining an anonymous function which uses that variable, like a capture. But yeah, a curried function is definitely a closure. Good to know. Partial application. Partially applying a function means creating a new function by pre-filling out some of the arguments to the original function. I know this as binding. What's up, Mads? Um, I know this as binding, but that's just because that's the name of the function in the language that I used when I was first exposed to this. That was C++. So yeah, we see that we take a function and some args, and then it returns a function that takes more args, and the function that we return simply calls the original function with the current args. So if we have this add3 function, what's up? Dude, I like that sweatshirt.
Thank you.
How you feeling?
Oh, I feel good, but I had a little too much fun last night.
See, man. So this add3 function will take three numbers and add them up, but if you partially apply 2 and 3, then you see that A and B get bound to 2 and 3, and we return a function that simply takes one argument and returns 2 plus 3 plus that argument. I guess there's a theme here. We're getting that 5 plus function in different ways. Check this out. That's the bind function on the function prototype in JS does this for you. Not sure what that null does. Yeah, that's fine. Yeah, curried function is pretty similar. and we are actually getting to currying. The process of converting a function that takes multiple arguments into a set of functions that take one at a time. Or not a set, like a list, I guess. Each time the function is called, it accepts one argument and returns a function that takes one argument until all arguments are passed. So you can think of like a process that binds the first and just repeats like that. So yeah, we could have made add 5 if we curried with 5, but they curried with 40, and so this itself returns a function object which immediately gets invoked with 2. So yeah, not too crazy. Auto currying, transforming a function that takes multiple arguments into one that, if given less than the correct number of arguments, returns a function that takes the rest. Okay, so that's interesting. The rest, I guess, is a like a list type. When the function gets the correct number of arguments, it is then evaluated. Lodash, a very famous JavaScript library that is namespace to this Lodash, and Ramda, which I've never heard of before, have a curry function that works this way. I guess Ramda is just a Lodash alternative. I've seen a lot of like NPM, updates where they're like updating this vulnerability in Lodash. So maybe it's like maybe the people want an alternative, or they're just doing it better. Hey, underscore, you're doing it wrong. That's interesting. That's probably going to be a cool link. I'll maybe check that out later. Function composition. The act of putting 2 functions together to form a third function where the output of one function is the input of the other. This is, one of the most important ideas of functional programming. All sorts of different ways to show this off. You can tell a good functional language from a bad one by how easy it is to express it. JavaScript not trying to be the best functional language. In terms of syntax, in terms of ability, no, it's pretty good. But anyway, so yeah, we're composing, getting the floor of it, and then taking it to a string. So yeah, we get this float, we floor it, and then to-string it. Pretty straightforward. You can think of this like a Unix pipeline. Unix pipelines like Shell, really, really good at composition. Everything is like supposed to go from one to the next. Continuation. At any given point in a program, the part of the code that has yet to be executed is known as a continuation. This is a definition that I am not familiar with. I've heard of a continuation, but I kind of thought that it applied to like pausable functions like a generator or a coroutine. But yeah, cool. Okay, so I'm going to go through this one a little bit more slowly. Here's a function that takes a number and just logs it. Add one and continue is, I guess it takes a number and a continuation or a paused function, and then adds one to number and calls the continuation on the result. So print as string, we continue with 2. Continuations are often seen in asynchronous programming when the program needs to wait to receive data before it can continue. Okay, so I've also heard the word like thunk, like a unit of code that is yet to be executed, but like it's kind of a parameter. Pretty similar to higher order functions. The response is often passed off to the rest of the program, which is the continuation once it's received. Okay, so like let's say you have a chain of promises where you need to do one operation, then the next, then the next. The first operation will return some result and say, okay, but I'm waiting on like someone else to say that they're ready for me to continue, and then here's my code. So like let's say that you write a function called wait for user input and return name. Like they type in something and you give them a name. So your function accepts 2 arguments: 1, a function to run, and 2, like a promise. And that promise has no value until someone fulfills that promise, and then boom, all of a sudden your continuation can run with the data inside the promise. Or if the promise fails, then of course the function needs to be able to handle that too. Okay, so continue with program that takes data, and we get an error and a piece of data that if the error we handle it, and then otherwise we do that. This is kind of what happens when you let's see when you want to return like more than one element from function composition. There's not always like one clean path to go. So you had better hope that your next function accepts the same number of arguments that your first function provides. So you can have like functions that compose a little bit more intelligently than just blindly passing it along. You can have a function that composes but first handles an error if possible and then passes along that. So normally you wouldn't be able to compose something that returns this with a function that takes this. But with intelligent composition, or like complicated composition, I guess, also known as like monadic composition, you can do extra work, all sorts of extra work between compositions. Um, Continuation. Yeah, I guess I still don't quite grok this, but the part of code that's yet to be executed. I guess that makes sense. Pure function. This is the best word. Function is pure if the return value is only determined by its input values. No side effects. No side effects. A side effect is basically like an implicit argument to a pure function. The function must always return the same result when given the same input. So yeah, I mean, I'm not even gonna go over this one because it's something that like you have to understand really deeply, and I'm not like this is not a deep dive into any of this. This is just an overview. So if you don't understand perfectly what pure functions are, study that, study that, study that, study that. Side effects. A function or expression is said. Why am I saying that? This is like a really simple concept. You can basically replace a pure function with a dictionary from input to output. But let's say that you have a global counter that you're incrementing, and the function is called like return time. Return time takes 0 arguments and returns a different time every time. So yeah, that's not pure. Pure composition is a lot simpler than impure composition, just because there's a massively smaller state space to deal with. Only pure functions are the exponential type. Impure functions are like, well, they're technically still the exponential type, but only if you consider the global variables that they reference as implicit inputs. So yeah, lame. Don't even worry about impure functions. Just don't avoid them if possible. Side effects. A function is said to have a side effect if, apart from returning a value, it interacts with external mutable state. So yeah, it's like kind of the opposite of a pure function in that impure function. Instead of reading external mutable state, we're setting external mutable state. And once again, if you can avoid functions with side effects, definitely do so. If not, so it goes. I think having multiple return values is a really like convenient thing to be able to do to avoid needing to do side effects, because instead of returning an answer and having a side effect, you can return an answer and the side effect wrapped in an object. Of course, you could also just return a struct that contains the answer and the side effect inside that struct, but whatever. It's all the same. Another thing is like out parameters, which, I mean, those are like kind of side effects. I would call them side effects, but if someone were to argue with me, I would hear them out at least. I wouldn't turn my nose up at them. Idempotent. This is a pretty cool word. Basically, reapplying it does not produce a different result. So if you send a GET request to a server and it like doesn't make it, you just retry sending it. So you should have some retry logic. But if a function, if the GET request is slow and you accidentally end up sending the GET request twice, like obviously it shouldn't do anything different. Now a POST request where you like add some data, that is kind of where you might get in trouble for sending something twice. Like let's say you're trying to register a new user, and the POST request returns like the user ID. So you might send the request twice because of a timeout, but then actually both of them happen to make it to the server and 2 users get created. That's bad. But if you write your code in an idempotent way, such as adding a request key, then it's super easy to realize that those 2 requests are in fact the same one, and the server can behave idempotently. So yeah, calling absolute value twice on the number 10 clearly doesn't change it. Same with sorting an array 2, 3, n times. Idempotency, it's like impotent, but better, because impotency seems like a bad word, I guess. But idempotent is a good word. Point-free style. Now, this is a little bit of a jargony piece of jargon, because the concept is like the etymology is a little bit more divorced than like all the other words. Like pure and impure, maybe that one kind of makes sense. Like higher order function, that one totally makes sense. Composition perfectly makes sense, but point free, less so. Argument free, now that makes sense. Like everyone could understand what an argument free style of like writing code is. Of course, you'd have to be a little bit comfortable with function composition to realize that you can in fact write useful functions purely through composition. But anyway, this ends up getting called point free or tacit. But that's just like historic reasons. Like it's like a really mathy branch that this like name came out of. So if you imagine like a tree where all of these concepts are getting discovered, all the like nomenclature or jargon that descends heavily through one branch of a tree and is like the core of modern programming, those are going to have words that we're all familiar with. But if you branch off back in like, you know, the 60s, then it might get weird. But that's fine. We're not just like machines here, we're engineers, and we like communicate with jargon, and that's the whole point of going through this entire document, is to learn all these weird things. So argument free style, also known as point free style. Writing functions where the definition does not explicitly identify the arguments used. Seems weird, but it's actually pretty cool. The style usually requires currying or other higher order functions, aka tacit programming. So here's a function called map that takes a function and a list, it's curried, and will return applying the function to every element of the map. And here's a curried add function. So this is not point free because numbers is an explicit argument. We are mapping the function add1 onto the numbers array. So it's just basically going to add 1. But here we can write the same function but call it increment 2 instead of increment all. And we're simply mapping the add1 function. And, you know, this isn't going to do anything like by itself, but you know what? Neither is this. This is just defining a function. Yeah, point-free function definitions look like normal assignments. It's worth mentioning that point-free functions are not necessarily better, as they can be more difficult to understand when they're complex. Yeah, I mean, I don't think that adding the numbers in this case adds readability. It's just clearly being a lambda here, whereas this is like, if you're not familiar with it, it's confusing. Yeah, I guess they're not necessarily better. However, you can generally write like a thunk, like a bit of computation in multiple different ways, and the point-free style will. I think it's like cleaner. It's gonna force you to be more direct. Whereas if you were to write it inside of a lambda, you could like have intermediate results and then pass that to this, and I guess, you know, it's not that huge of a difference. But if you can write something in point-free style, I recommend that you at least do it so you can look at it, and then you can decide whether you like the point-free style or not. It all depends what is more readable. Always emphasize code readers over code writers, just because in 2 months you're going to be a reader, not a writer, of even stuff that you wrote. So a predicate. Yeah, this is like a really nice little word. It's basically just a function that returns true or false. Normally named with is, so like is top, or like is first, or like, you know, is blue. These are all predicate functions, and you don't need a special name for this, but once again, because we were talking about math before we're talking about programming, that word existed, and you know, it's useful. Just as you should prefer pure functions over impure functions, you should prefer predicates over more complicated functions that return like more stuff. Because really, at the end of the day, if you only need to return a Boolean, don't do anything more complicated. An additional thing is like, yeah, there are a lot of functions that accept predicates. Higher order functions that expect functions that return Booleans. Yeah, functions that accept predicates. Just a different way of saying the same thing. So for example, it returns true if a is greater than 2, and then will filter in everything that passes the predicate. You map it over and then basically use that mask that you create to, you know, accept values or not. Contracts. Not familiar with this one. A contract specifies the obligations and guarantees of the behavior from a function or expression at runtime. This acts as a set of rules that are expected from the input and output of a function or expression, and errors are generally reported whenever a contract is violated. Oh, okay, I think I get it. So if you have a weakly typed system and you want to ensure that it acts with strict typing and you don't want to rely on a compiler, you can enforce that at runtime. It seems less efficient, but you know, I can't be like always use strict typing because that's just like a stupid thing to say because some people don't and can't and whatever. But always use strict typing. Anyway, contracts. This is kind of looking like a constraint or like a concept in C++. But anyway, make sure that the value is a number. So add one and we accept anything because it's JavaScript duck typing. That's how we roll, baby. Contract it to be a num and then return +1. This will throw a runtime exception because we can't do it at compile time because that's just the world we're living in. But ideally, this would be caught at compile time and contracts would not be necessary. But otherwise, adding this, it incurs a performance hit. But if you're not using strict typing, you probably don't care about that. You're just trying to like move fast and get shit done. So yeah. Category. This is a big word. It's pretty cool. I wonder how they're going to explain it. A category in the branch of mathematics called category theory is a collection of objects and morphisms between them. Morphisms being like objects being like dots and morphisms being arrows, and category being a collection of dots and arrows. In programming, typically types act as objects and functions are morphisms. So when I say functions are the exponential type, let's say that you have a function that accepts like n arguments, like a Boolean would be 2. So I meant like n as the type, not n as the arity. And you return, once again, a Boolean. So for every possible input, there are the entire output of possibilities. So if we, let me change the numbers actually. So let's say that we have a enum of type 3 returning a Boolean. So if we were to create every single pure function that can have that type signature, we would create pretty much how many dictionaries? The first dictionary would take any argument and return all zeros for each one of them. So the first one becomes false, the second one becomes false, the third one becomes false. The second one would return false, false, true, and the third one would take false, true, false, and etc. So for every possible input to the function, we have all of the outputs as a possibility. So 2 outputs for the first function, 2 outputs for the first argument that's possible, 2 outputs for the second argument that's possible, 2 outputs for the third argument that's possible. That is, you take the number of possible types of the output and you raise it to the power of the number of possible types of the input. So that's why it's the exponential type. So there are 8 possible functions that accept 3 arguments and return 2. Or accept an enum of 3 types and return a Boolean of 2. So yeah, you are basically defining you are defining 8 morphisms when you write that function, which is pretty cool. Like you're defining a whole slew of arrows just by having 2 existing objects and this one function. So if you define every value as a different object, that's going to be a ton of arrows. But if you only define types as those objects, then you're only going to be drawing 1 arrow per function. But yeah, anyway. In programming, typically types act as the objects and functions as morphisms. I'm going to open up a talk using types effectively, Ben Bean. This is, it was just there. Did I spell it wrong? This is the talk that you should check out if what I was saying about all that doesn't make sense. And then there's also category theory for Programmers by Bartosz. Oh, I'm just spelling everything wrong, aren't I? By Bartosz Maluski, and this is like a math class instead of an hour-long like talk about it, but still totally cool. Oh, I see. Connor Hoekstra wrote or made this playlist, which is super nice. But yeah, okay, cool. So these are the 2 recommendations, and we'll get back to it. To be valid category, 3 rules must be met. I'm not going to go over this because all of those things do it, and like a category isn't inherently interesting or useful until you kind of like get why. So yeah, value. Anything that can be assigned to a variable. Yeah, I mean, you have a type, it has n possible values, and that's like a useful way to think of types. Constant. Variable that cannot be reassigned once defined. Referentially transparent. That means they can be replaced with the value they represent without affecting the results. Okay, that's cool. I'm kind of thinking about pure functions being referentially transparent with dictionaries or hash maps or maps or like whatever you want to call that data structure from key to value. Um, yeah. Okay. Cool. A constant function is a curried function that ignores its second argument. What? We accept A and a unit and return A. Why? Oh, that's like the identity function. It just like doesn't do anything. Okay, so that's interesting to call it a constant function, and it's also interesting to define it as a curried function that ignores its second argument. I would just say it just returns itself. Whatever argument it gets, it returns that. It's really important to have a like an identity in a category, identity morphism for each object to itself. Maybe it's a mistake to skip category. I'll just read all of this then. A category in category theory is a collection of objects and morphisms between them. In programming, typically types act as the objects and functions as morphisms. To be a valid category, 3 rules must be met. There must be an identity morphism that maps an object onto itself. This ends up being really useful when you're trying to compose stuff, and you end up wanting to not do stuff in the middle of composition. So you have to like have a function that returns self instead of just using self, because a function that returns self is of type function, and self is of type whatever self is. So it's a little bit of like type wrangling, and it just ends up being notationally very convenient. Where A is an object in some category, there must be a function from A to A. Morphisms must compose. Where A, B, and C are objects in a category, and F is a morphism from A to B. Draw this graph in your head, by the way. Draw those 3 points. They're in a triangle. A to B is one leg of the triangle, and G is a morphism from B to C. That's the other leg of the triangle. G composed with F on the value X must be equivalent to G. Yeah, it's just saying that calling them one after the other is the same as composing them. Using this binary infix composition operator instead of the JavaScript notation may look like it's not saying anything else, but let's remember this is a math thing. So think about all the branches of thought that peeled off in the 60s before like we started thinking in terms of this notation. And then maybe hopefully you can respect this dot just as you respect a plus or a multiplication or whatever. Composition must be associative. Yeah, starting to look a lot more like the plus operation, but whatever. Yeah, composition being associative means that if you start from it's just the third leg of the triangle has to exist, and you have to be able to find the third leg of the triangle from the first 2 legs of the triangle. And you can kind of see, like, if you array it in a map in your mind, that the 2 arrows might represent like transformations, like 2 to the right, 1 up, and you can add those vectors and end up finding a third vector. Not even like talking about them in relation to the first 2 vectors, but it's its own vector. It's a completely new vector. What comes after G in the light? A, B, C, D, E, F, G, H. Yeah, just like H would be the third function that equals G compose F. I forget if it's G compose F or F compose G, whatever. An example, we can define a category. As an example, we can define a category max as a class. Yeah, the rules governing composition are very abstract. Category theory is great at uncovering new ways of composing things. So like when I said monadic composition way back when, like a monad is a mapping uh, from like, oh geez, not from category to category. What is it? It's yeah, I can't I am not I don't have a strong enough grasp. I'm thinking about it. Um, it's like an endofunctor. It's a monoidal endofunctor in a category, which like monoid is a word that we'll get to, but it's basically like if you have a binary function and a set of values, and you want to keep applying that binary function, like you can compose it just like that. You can do like a reduction or like a left fold, like something like that, where you take a list of the values and the binary function and you plop it in between every single one of them, and it makes sense. A monoid needs to have a couple things, just as a category needs to have a couple things, and the monoid needs to have a type with all sorts of values, needs to have a binary operation, and one of the values needs to be the identity value given this binary operation on that type. So like plus 0 times 1. These identity values mean the binary function doesn't change anything. And the last thing that a monoid needs to do, not obviously, but unsurprisingly, is that it needs to go from one type to that same type. So in terms of types as objects, it is an identity function. But in terms of values as objects, it's called closed, where given values inside the type, it will output values also inside the type. Just like, modular arithmetic, all sorts of stuff. So a functor, you can think of it as like wrapping a type. It is a type that is parameterized by another type. So a list of ints, a maybe Boolean, maybe being the sum type of either it's there or it's not. Either it's a value, a bool, true or false, or it's invalid. So it's sum type plus 1, SUM, sum type. Although ironically, the maybe type has the sum value, SOME. Maybe that's a pun now that I'm thinking about it. It's either some bool or none. So 3 types. You can think of that as an enum of 3, or you can think of it as a maybe bool. Why was I even talking about that? Gosh. Oh yeah, functors. So you can wrap a bool in a functor, and as you can imagine, like the monoid's binary operation doesn't accept a sum bool, it accepts a bool. So when you need to unwrap during composition and you need to do something a little bit more intelligent, it requires that like special type of composition where you do intelligence and then compose. So you can compose a bunch of bool comma bool to bool functions, even if you have a bool comma bool to maybe bool functions with monadic composition and all that. Anyway, I'm getting ahead of myself. So max category. You get a constructor where you set a value and an ID returns itself. Composing it with B will return the larger object, and toString will just represent it as a string. So max of 2 and 3 and 5, getting the ID of that twice, idempotent operation, will of course return 5. So you can kind of see how this is a pipeline. Another way to write this would be a list of 2, 3, and 5, and then dot max it. But like when it's a category, these purple values, the function names, like they always exist. It doesn't have to be specific to the max operation. You could define composition however you want, and that starts to get really powerful when you realize that it's so vastly, wildly general that it applies to like almost anything. Oh wow, is this? Yeah, this is Bartosz Milewski. Okay, of course. He's like kind of the gold standard for what this is. Okay, we already said value and constant. Constant function, yeah, I was shocked about that. Constant functor, object whose map doesn't transform the contents. What? Oh, I see. Okay, so we have a constant of 1, and even if we map a function on top of it, it still just returns a constant of 1. We'll get to functor eventually. We'll get to monad eventually. Yeah, chain. You don't call it compose when you're doing intelligence, or you can call it composing, but it would be called Kleisli composition after the mathematician. Yeah, shocking. We're naming stuff after old mathematicians instead of like comfortable programming language, but get used to it. It's like the math side of stuff. That's why we're learning all the jargon. There's multiple different ways to say all of this stuff, so it's useful to have A, the ideas down, and B, all the language. But unfortunately, like they're so intertwined that it's hard to get the ideas down without the language, and it's hard to get the language down without the ideas. So yeah, good luck. You'll get there. It takes time. Oh, now finally we get to functor. This is a really important one, and it's honestly one of the bigger, like, in my opinion, to grok, um, like functional programming. It's an object that implements a map function that takes a function which is run on the contents of that object. So you can kind of see it implies that there's like wrapping, but it doesn't directly state that. Why? Well, because in reality, a functor is defined mathematically like this. But in practice, the wrapping conception of it is kind of nice. A functor must adhere to two rules. Um, it preserves the identity. So if you map the identity function into the functor, then it's as if you've done nothing. And also, it's composable. So if you have a set of composed functions that can operate on a type, then a functor of that type can also accept that composed operations. So just as we discover H and pass in H, like if this was written point free, it would make a lot more sense in my opinion. But the arguments are kind of getting in the way. So if we define the function H as G compose F and then map H into the object, it's going to be the same as if we mapped F into the object and then mapped G into the object. So let's say we have a maybe int and we're mapping in the +1, then the +2 function. At mapping in the +1 function, we'll get the number +1. Mapping in the +2 function, we'll get the number +3. Whereas if we composed +1 and +2, those curried functions together to get +3, mapping that +3 in directly would get us the same result. Functors are like they're almost not a type transformation, but they totally are. Two perspectives. Take one perspective where they're a type transformation and it's completely different. A maybe bool is not a bool. A maybe int is not an int. On the other hand, it's the same thing. It's just a little bit of extra metadata. It's, you want to avoid side effects. You want to avoid having multiple values that you're throwing around. So you wrap it up in one object and there, you're good to go. And you can also have something like a list, which is like actually a completely fundamentally different data model than a single element or a maybe single element. So it's not, a functor is not so one-dimensional as simply wrapping a value, but it is a value parameterized by another value that preserves identity, and you can do all this nice composition stuff, just the same as if you weren't. Yeah. So let's see. The reference implementation of option is a functor as it satisfies those rules. Yeah, here we have sum, S-O-M-E, being the sum S-U-M type of +1. Yeah, pretty normal stuff. Pointed functor, no idea what that is. An object with an of function that puts any single value into it. Okay. That's fine. I don't know why this needs to be a word. I'm trying to think. Array of one, sum of one. I guess that's just a nice thing to be able to say. I'm assuming point is unrelated to point free. But maybe it is, because it could be like argumented function, a single argument functor, whatever. Anyway, I'm done with that. Lifting is when you take a value and put it into an object like a functor. Yeah, you could also call this wrapping, but lifting, imagine like the base type as like the lowest level, and then every time you put a functor around it, you're lifting it up by one type. And so this like really nice bottom level composition of like completely going left to right, it's all of a sudden broken because you're lifting up, you're a different type, but it's not so different that it's a completely unrelated type. So we're basically adding the y-axis instead of just the x-axis of jumping from value to value of a given type. So lift is then the word. If you lift a function into an applicative functor, then you can make it work on values that are also in that functor. Okay, I don't know what applicative functor means, but I know that it's like an important concept, so I'm just going to skip ahead to it. Let's see. Oh, applicative functor. An applicative functor is an object with an app function. App will apply a function in the object to a value in another object of the same type. So here we have the add1 function, and we apply it to an array of just the number 1. Okay, so an applicative functor reduces, let's see, ACK. I don't know what ACK stands for. Maybe it's accumulator, or we're concatenating the x's, and we're mapping the function onto it. Okay, yeah, it is accumulator. So we have all of our values. This is 1 in this example, and we're mapping f onto it, f being this, and then we put them in there. So I guess that if we were to have a list of these functions, it would apply them each in turn. This is useful if you have 2 objects and you want to apply a binary function to their contents. Ooh, looks like I'm wrong. It's not applying them in turn. It's applying them on the entirety. So add onto arg1, it should be 1 plus 3. Oh, that's cool. It returns functions. So it's like currying them. And then when we put it to there, I would expect it to return 5 and 8. But instead, we're getting 5, 6, 7, 8. So what's up with that? Oh, because this plus 1 applies to the first one. So we have 4 plus 1 is 5, and then 5 plus 1 is 6, and then we're applying this function to the second one. So 3 plus 4 is 7, and 5 plus 3 is 8. Okay, so it actually looks like it's doing both. An applicative functor applies a function in the object. So here's a function in the object, and here's the object, to a value in another object. Here's the other object of the same type. It's both the list functor, but they're parameterized differently, so it's hard for me to understand that these are the same type, because I'm thinking about C++, where one would be a vector of function, and the other would be a vector of int. But I mean, realistically, they're both just vectors, both just arrays. So yeah. So let's think about this again. We only apply, we apply that arg1 as the argument to the add function. We apply 1 as the argument to this function. I don't quite see where this is useful, but I know that applicative is a type class in Haskell. So it's like you have to prove something is applicative in Haskell, and then you can start using it all over the place, and it just lets you do all sorts of stuff. So yeah, okay, moving on. If you lift a function into an applicative functor, then you can make it work on values that are also in that functor. Yeah, that's what we just saw. We saw that the a to a plus 1 function was lifted into an applicative functor, a list, and then it was made to work on values that were also in that functor, the one that was inside that list functor. Some implementations have a function called lift or lift a2 to make it easier to run functions on functors. So note that it's apply and not map. So a.mapf, we apply f to every element in A, and then we apply b because we've returned a functor. And it could be partially applied. It doesn't necessarily need to be a value yet. Okay, interesting. Okay, I don't quite get it yet. And then multiply, we have this point-free multiply. This function now works on functors like arrays. So lifted multiply on 1 comma 2 with 3, and we apply the array 3 to the map of functions. And the map of functions is because we have curried the multiplication function onto this. So we have, what is it called? A closure. We have 2 closures after this, and the closure is 1 times b, accepting 1 argument b, and the second closure is 2 times b, accepting an argument b. And then we could map 3 into applying there, but that's what this does. This bracket 3 does that. And then, yeah, we got that lift A2 of addition, where here is our data. We create the partially applied add 1 and add 2 functions, and then we throw 3 into the add 1 function, and then we throw 4 into the add 2 function. Okay, lifting a 1 argument function and applying it does the same thing as map. Yeah, that makes sense. Lifting a 1 argument function, here's the 1 argument function, and then we're applying that. It's the same thing as mapping that function onto it. Okay, so yeah, a very roundabout way it seems, but once again, this is to increase the generality. Lifting simple values can be simply creating the object. So this is what I'm familiar with. This is what I thought that this was all about. Little did I know you can also lift functions. And lifting functions, God, that's confusing. Okay. I'm trying to think of all the arrows and the shape in my head, and it's not quite there, but that's all right. We'll get there. Referential transparency. An expression that can be replaced with its value without changing the behavior of the program is said to be referentially transparent. So check out this greet function. It's a function that returns a string, but I mean, we could just change it to a string. Once again, oh yeah, pure functions, totally relevant. And equational reasoning. Don't know what that is, but we'll get there. Yeah, broken if it depended on external state, like configuration or a database call. Impurity totally ruins this. And once again, functions, the exponential type, can be referentially transparent with dictionaries. For every possible value of the input type, we have all possible values of the output type as available. So a function that goes from A to B is of cardinality B to the A. And a Boolean is of cardinality 2, an int of cardinality 2 to the 32, 2 to the 64, whatever. Equational reasoning. When an application is composed of expressions and devoid of side effects, truths about the system can be derived from parts. Okay. You can also be confident about details of your system without having to go through every function. Yeah, so grain to dogs is going to take chicken into dogs and grain into chicken. So grain into chicken, chicken into dogs, and we get grain to dogs. Okay. In the example above, if you know that chicken into dogs and grain into chicken are pure, you know that composition is pure. That's the equational reasoning. So you can use equational reasoning for kind of slightly more formal proofs, and formal systems. Formal systems is kind of a cool thing that you can do with that. Learn TLA. Yeah, this is Hillel Wayne. This guy's a beast. He is just fun to listen to and all of his weird thoughts. And yeah, basically, what would I want to say about this? Let's say that you have a sorting function, and you're oh, the sorting function, it should never change the length of the list that I'm sorting. You might want to write that as an explicit test case if you don't have functional programming. But if you can be certain that every operation individually that you're using doesn't change the number of elements in the function, like map's not going to do that. Apply might, but map won't. Then you don't need to write that test case. Generally speaking, that test case doesn't get written anyway, but it can get more complicated and more interesting. Anyway, lambda, an anonymous function that can be treated like a value. Yeah, this is kind of something that was super complicated back in the day. Not back in the day, but was complicated for me to learn when I was younger. But now it's just totally something I can think in terms of. It's like a thunk. Not quite a thunk, but whatever. Yeah, so this function doesn't have a name, but it does stuff, and there's a really nice syntax to write it now because it ends up being so powerful and useful. Often passed as arguments to higher order functions. Um, yeah, instead of iterating through this and applying this every time and keeping track of a counter, just describe the thing you're doing. And you can assign lambdas to variables. This is basically giving them a name, but it's slightly different. Lambda calculus, a branch of math that uses functions to create a universal model of computation. I'm not going to get into this because I don't understand it. And also because the way that lambda was used like back in the day is slightly different than now. And yeah, anyway, it's cool, but I don't get it. So I'm not talking about it more. Um, Functional combinators. A higher order function, usually curried, which returns a new function changed in some way. Functional combinators are often used to point-free style, especially to write terse programs. So the C combinator takes a curried two-argument function and returns one which calls the original function with the arguments reversed. So this is just all like notation. It's this is the stuff that APL excels at, and if you want to write like really terse code, you find that combinators are actually like a pretty common thing to do. So yeah, if you have the divide by, I mean, this is like totally contrived, and I actually think this is not the best way to show this off. But like you have this divide by 10 function that you've curried for whatever reason, but you want to have it be the denominator instead of the numerator. So you can, yeah, like you can just do that, I guess. Yeah, because you're implicitly taking the numerator as the first argument. But yeah, like for example, let's say that you have like two objects and you want to like compose them one way on the left side and the other way on the right side, and then combine those two values. The C combinator would be invaluable, and of course the fork combinator, or like I think it's the psi combinator, that takes two arguments and then a function. You would use the psi combinator on the C combinator one side, not C combinator on the other. So that's just like a thing. Lazy evaluation. You don't evaluate until you need to. You're lazy. It's a call by need evaluation mechanism that delays the evaluation of an expression until its value is needed. So instead of like if you say A of 5 or like F of 5 and you pass that as an argument, like why do any computation until A actually gets used? Maybe like some other part of the function will end up making the value that you get from F when given 5 is redundant and it's never even used. So it makes a lot of sense to delay computation. Like functional programming just totally lets you be lazy and parallel. It divorces how you do stuff from what you want to do. So it gives an intelligent execution engine a lot of power. Golang is kind of similar. You define all of your asynchronous little Go functions or Go routines, and the engine will be smart about how to allocate and share like whatever and do stuff. So yeah, it's kind of cool. Lazy evaluation. Think of this as, I guess, like similar to continuations in that regard, but in the other case, it's like in the other regard, it's like totally unrelated. But whatever. In functional languages, this allows for structures like infinite lists, which would not normally be available in an imperative language when the sequencing commands is significant. Yeah, Python 2 to Python 3, the range function turned into a generator, and the generator is lazily evaluated. So you can say range of 1,000,000, and you don't even use any memory until you actually say next. Yeah, they have an iterator here. They're yielding. Yielding is just what a generator in Python does. Coroutine. So that's kind of like if a single function can return multiple results, it's a coroutine. That's lazy evaluation at its like finest. But the execution engine that I was talking about, where you pass f of 5 as an argument and it doesn't get evaluated until it's used, is like different. Oh, here we go. Monoid. I guess I should have been more patient. An object with a function that combines that object with another of the same type. Yeah, mathematically that is called a semigroup. But it is a semigroup with an identity value. So yeah, the identity value makes it really, really useful. I can't explain that better, but that's not because it's complicated, just because I don't have a stronger grasp. A simple monoid is addition of numbers. In this case, the number is the object, and plus is the function, and the identity is 0. Yeah, must be commutative too. It's also required that the grouping of operations will not affect the result's associativity. Are monoids associative? I guess they are. Oh yeah, of course they are. Of course they are. Um, Array concatenation also forms a monoid. But uh, that's not associative. Array concatenation is not associative. So I think it's still a monoid, but it's just not associative. I'm not sure. Whatever. The identity value is an empty array. Yeah, of course. As a counterexample, subtraction does not form a monoid because there's no commutative part. A monad is an object with of and chain functions. Of is kind of like a lift, or like it's like to create that. It's to create the monoid. It's like to like wrap the value in the monad, and it has chain functions. Chain is like mapped, except it unnests the resulting nested object. So instead of just purely applying it to the value that is the monad, you strip away the wrapping part and operate on the value inside. So let's say that you have like an either or. That is like you either have a left or you have a right, and that's the type. So chaining can only work. You can make a chain called that only works on the left side, and that's basically it would be the same as just map. Or you could have a chain that only works on the right side, and once again that would just be like map. But you could say, oh, if it's a right type, then we give up, and if it's a left type, then we continue. And that would be a chain that is unlike a map because it does stuff that is more intelligent and requires like all the values there. Anyway, so prototype on array to chain a function, it's reducing the accumulator and iterator where we're concatenating onto the accumulator the function on the item, not iterator. Yeah. So cat comma dog, an array of cat comma dog, and an array of fish comma bird. We chain a where we're splitting the comma. It will return one array, and then it will return another array. And because we're just like unnesting those values or unwrapping them, we end up with two individual values that we are concatenating into this. And so we have that, and then we concatenate the two more values onto it, and yeah. Oh, I should have read ahead. Contrasting this to map, where we are not lifting the values out. We're not doing anything more intelligent than pure function composition. Here we're doing a little bit of logic. So yeah. Basically, this chaining for arrays looks like flattening. Oh wow, look at that. Chain is also known as flat map. And it's also known as bind in other languages. Of is also known as return in other functional languages because you have a value and you want to return a monad. It's also known as pure. You have a value and you get a pure monad in it. I don't quite get that one. I totally get flat map. I think that's the most intuitive way to call chain. It's also known as Kleisli composition or monadic composition. Not to be confused with compose because of the same reason that map and chain are different. And bind. Why is it called bind? Oh gosh. At one point this made sense to me, but I've since totally forgotten it. I'm imagining the like shape that a monad is. It basically takes a function that like lifts. It's basically like a function that takes a value and returns a lifted value, and then you can think of a bunch of arrows from the bottom to diagonally up because to the right means you're getting a new type. To up means you're changing the type. Another value of the same type is the right. New type is up. So it's diagonally up to the right, and you have a set of those, and they don't compose well. But when you're chaining, you like bridge that gap. Let's see. Train track compos. Sorry, can't find what I'm looking for. Comonad, an object that has extract and extend. So you can extract the value out of a functor, and extend runs a function on the comonad. The co prefix is pretty common, like variant and covariant. It's just like basically the same thing, but different. So I don't know why semigroup and co-semigroup aren't called that way. It's just called semigroup and monoid, but whatever. So it goes. The function should return the same type as the comonad. So we take a comonad and we extract it, then add 1, and we get that. It looks pretty similar to .fmap, but I guess fmap being apply a function into a functor, but whatever. Kleisli composition, an operation for composing two monad returning functions. But those monad returning functions are those diagonal up arrows that don't link nicely, where they have compatible types. In Haskell, this is the fish operator. So using option, we can Kleisli compose that by saying if it's sum A, return that, otherwise return none, and Kleisli compose, we call it, and then chain it on G, and chain, none dot chain anything is just going to be none, otherwise it applies it like faithfully. So lots of stuff going on here, a lot of stuff in Kleisli composition. But it's like a pretty basic thing that a basic thought brick, but complicated to like work up to. But it's totally cool, and once you like grok it, it changes how you look at stuff, because you're real happy to write all of those diagonal functions that like return monads and just can compose like no one's business. You basically turn composition in every case into just the chain operation on a monad. So all of the logic, if like your error condition or side effect or whatever can be expressed via a monad, then you just write the chain operation once and you get all of the power, all of the error checking, all of the logging, all of the whatever you want to do during function composition for free. And so it's super tight. It's really fucking tight. Okay, we're back to an applicative functor. An object with an apply function. It applies a function in the object to a value in another object of the same type. Yeah, so I guess this is like when you have a raised function, a lifted function. It's like wrapped in that functor and you get to do stuff. Yeah, I'm not going to go over this again. A morphism. I don't quite get it, but I'll get there. A relationship between objects within a category. In the context of functional programming, all functions are morphisms. Yeah, just like arrows. Arrows, man. Homomorphism. A function where there is a structural property that is the same in input as well as the output. For example, in a monoid homomorphism, both the input and the output are monoids, even if their types are different. Okay. To list A, and it joins in with a comma. Array is a monoid. It has a concat operation. Yeah, okay, I get it. Like it's basically this. It's like it's almost isomorphic. Oh, interesting. It's a more general type of isomorphisms. Endomorphisms are morphisms within a category. Isomorphisms are morphisms between categories where like they're just the same. So it's like let's see, what is an isomorphism? Like representing addition as just a list of numbers versus a string of numbers with a comma separating them. Wow, yeah, that's literally just this example. I can't think of a single isomorphism right now. It's too general. It's just, I guess an isomorphism would be an ebook and a book. They're the same information, same ability to do operations, to read, to turn a page, to talk about it, to, whatever. But anyway, a homomorphism is more general than an isomorphism because it includes endomorphisms. This looks cool. Oh, it's a whole ebook. I don't need to learn functional programming again. Oh well. A function where the input type is the same as the output. Since the types are identical, endomorphisms are homomorphisms. Isomorphism, a morphism made of a pair of transition between two objects that is structural in nature and no data is lost. 2D coordinates can be stored in this array or as an object. Yeah, perfect. Personally, I find this more readable. That makes a lot more sense because this could be anything. It's more general. However, what do you think is easier to work with if you want to, I don't know, do something? Up to you. You do your isomorphisms freely. They're an interesting example of morphisms because more than a single function is necessary for it to be satisfied. Yeah, you have to isomorph to the left and to the right. Isomorphisms are also homomorphisms since both inputs and output types share the property of being reversible. Catamorphism. Never heard of that. A function which deconstructs a structure into a single value. Oh, you're concatenating them. Reduce right is an example of a catamorphism on array structures. Reducing is like that's the man right there. That's like totally shows up everywhere. Stood algos reduction. There's like this talk where all these stood algorithms are implemented in terms of reduction. But I can't find it. C++, most stood algorithms implemented in terms of reduction. Yeah, I can't find it. That's fine, whatever. Sum is a catamorphism from a list of numbers to a single number. You're kind of concatenating them. I mean, it makes more sense when you think about concatenating them, but a reduction is not concatenating them. It's applying a function in between all of them. Anamorphism. Oh, and of course, number has to be a monoid for this to be successful, like available even. A function that builds up a structure by repeatedly applying a function to its argument. Unfold is an example which generates an array from a function and a seed value. So like, let's say you have a random number generator and you unfold it like 5 times. You apply the next operation 5 times and you get 0, 1, 2, 3, 4, and then the 5th element of that random number generating sequence. This is the opposite of a catamorphism. You can think of this as an anamorphism, as anamorphism builds up a structure and catamorphism breaks it down. I guess it's kind of named like cation and anion. Cat, I feel like, is plus and an is minus in terms of like types. And I guess is the cation positive? That would yeah, I guess that makes sense. I guess it's not concatenation. Or maybe cat and concatenation and cation and catamorphism all have the same root, where cat is like plus or something like that. Cat Latin root. That would make sense, actually. Wow, okay. Upwards in place in time, backwards back against. Yeah, there we go. And then we'll try cat. Really? Sad. Oh well. Yeah, okay, cool. Anabolic, yeah. I like anabolic metabolism. Okay. Yeah, unfolding a seed, you just apply function to the seed multiple times and generate that. Countdown, unfolding, where you return either undefined or the value, and then n minus 1. Yeah, 5. Then okay, cool. Hylomorphism, the function which composes an anamorphism composed by a catamorphism. So you're unfolding and then folding. That's kind of funny. I have no idea. I've never seen this before. I don't think this is a generally applicative word. If you hear someone use it, I don't know why that would be like the best way to say stuff. But okay, I mean, it's jargon. Like, it exists. Use it if it's relevant. Paramorphism, a function just like reduce right. However, there's a difference. Your reducer's argument are the current value, the reduction of all previous values, and the list of values that form the reduction. Oh, okay. So just slightly different like type thing. This is totally what we used all the time when we were writing ML, like OCaml, in my college class on programming languages. But like, yeah, I don't know. Like it's just it's like side effects don't exist globally. They exist as the argument. Obviously not safe for lists containing undefined, but good enough to make the point. Oh yeah, that's fine. So we get a reducer, an accumulator, and all of the elements, and we paramorphically do the next level of recursion. So that's kind of cool. So we can return all the suffixes just like that. Nice. The third parameter in your reducer, x, and then spread of the rest of x's is kind of like having a history of what got you to your current acute. Yeah. Okay, that makes sense. Yeah. So if you're like returning a path, you're going to use a paramorphism because you need to keep track of the path that got you there, like what in case you need to backtrack. Yeah. Apomorphism, not an aphomorphism or aphorism. I mean, the opposite of a paramorphism, just as anamorphism is the opposite of catamorphism. With paramorphism, you retain access to the accumulator and what you've accumulated. Apomorphism lets you unfold with the potential to return early. I actually don't get that, but it doesn't have an example, so the guy must have not thought it was important, so whatever. Let me just think about it for one more second. You retain access to the accumulator and what has been accumulated. Okay. With the potential to return early. Setoid. Sounds like monoid, but for sets, I guess? I don't know. I don't really know what the mon part of monoid is. An object that has an equals function which can be used to compare other objects of the same type. To make an array a setoid, we write the equals function, where if they're not the same length, we return, and then if each element is not the same, we return. Otherwise, if they're the same length, all the elements are the same, true. Seems like a setoid is just like has deep equality. I would say deep equality, but setoid, yeah, sure, use that if you want. An object that has a concat function that combines it with another object of the same type. So this has a binary function that is closed, that is given two arguments in a type, you return an argument in the type. Without the identity, it's not a monoid, but it's still a semigroup. Group theory is a whole branch of mathematics that existed for a while. Foldable. Any object that has a reduce function that applies a function against an accumulator, and each element in the array left to right reduces into a single value. So think of a whole, like a long, like a receipt of paper. It's very long, and you fold it, fold, over and over. And every time you have accumulated that stack of receipt paper on the left, you can fold it one more time to the right. Fold it one more time to the right. And yeah, 1 plus 2 plus 3, folding it all the way, reducing it into 6. Folding, reducing, think of them pretty similarly. Lens. Now, I have no idea what this is. This seems like a basic concept, so it's kind of cool. It's a structure, often an object or a function, that pairs a getter and a non-mutating setter for some other data structure. What? A non-mutating setter? Maybe it just returns a new object. A getter for object name or property, and a setter. Yeah, okay, there it is. It's just like a reference, basically, where you can read it and you can assign to it, but when you assign to it, you have a new object. So it's really good for immutability, really good for maybe caching or like not fucking up via side effects. Oh yeah, not fucking up via side effects. There it is. Having the pair of get and set for a given data structure enables a few key features. I guess R is a lens. Oh, it's Ramada, so it's like Lodash. It's just that functional library. It seems to have a more of a like a formal kind of feel than Lodash. Lodash is just like do work. It happens to be the case that functional programming is the easiest way to do work in a lot of cases. Not all the time, but when it is, I mean, use it. Come on. Why are you iterating over 1 to 10 or 1 to object length when what you really want to do is just map? Whereas Ramada will be more formal and have like a lens. So you can view the name lens of the person, name being name. You can set through the name lens and it returns a new object. And you can even invoke a function and it once again will return a new object. So you're not going to mutate person. Oh yeah, they even have it marked as const, of course. Lenses are also composable. Of course they would be. Why wouldn't they be? I mean, it's all functional. It's all composable. Easy immutable updates to deeply nested data. Yeah, there we go. I'm not even going to go over that because that just makes sense. Type signature. Ooh, this is a classic. This is like just a really fundamental thing, and it's simple. Other function, you probably know this already. Often functions in JavaScript will include comments that include the types of their arguments and the return values. Poorly typed language. There's quite a bit of variance across the community, but they often follow the patterns. This is Haskell style with the 2 dots and the single arrows to represent currying. If a function accepts another function as an argument, it's wrapped in parentheses. Right, because that is a single type, believe it or not. Letters A, B, and C are used to signify that the arguments can be of any type, classic Haskell. The following versions of map take a function that transforms a value of some type A into another type B, an array of values of type A, and returns an array of values of type B. So given A and B, we return a function from list of A to list of B. Or is it given a function from A to B, we return a list of A, a function that takes a list of A and returns a list of B. This is... I recognize this function signature. I believe it is bind, but I don't remember. So whatever, we can move on. Algebraic data type. I fucking love this concept. I've been talking about it the whole time. A composite type, so it's composed of stuff made from putting other types together. Okay, well this is redundant, but that's fine. It's a composite type. It's a type made from putting other types together. Why use this jargon if you're going to redefine it in the immediate sentence? I don't know. 2 common classes of algebraic data types are sum types and product types. Oh, I guess that's just right here. I've gone over this already, so I'm not going to go over it again. it's like a big concept. So just because I'm skipping past it doesn't mean it's not important. And it is something that like you need to think about until you can grok in terms of it. But yeah, sum type, product type, and then functions as the exponential type. Option. An option is a sum type where it's just sum plus one. Function. Well, we all know what functions are. A function where the type is from A to B is an expression, often called an arrow or a lambda expression, with exactly one immutable parameter of type A and exactly one return type of type B. Oh, this is the math definition of function, not the programming version. That value depends entirely on the argument, making function context independent or referentially transparent. Yeah, so the math type of a function is pure. What is implied here is that a function must not produce any side effects. A function is always pure by definition. These properties make functions pleasant to work with. They are entirely deterministic and therefore predictable. They're composable. You can do all sorts of fun stuff with them. Functions enable working with code as data, abstracting over behavior. Yeah, mapping times 2 onto an array. Pretty straightforward stuff. A partial function is a function which is not defined for all arguments. This is a really useful thing to write and then use to create an actual function, especially if you got like a monad going on. So you might write a partial function and then have a contract that instead of throwing a runtime exception will return a none type for the stuff that the partial function is not defined on. And then where the partial function is defined, obviously you just do the normal thing. It might return an unexpected result or may never terminate. Partial functions add cognitive overhead. They are harder to reason about. You can fuck up with them, and they can lead to runtime errors, which is like if you have a runtime error instead of a compile time error, then you're spending a lot more money on fixing it like an idiot. So just, use your compiler to catch all that shit. And you can use a compiler to catch all that shit if you define your partial functions as, parts of a monad with types and like strictly blah. It's great. Don't ever have partial functions. Always have functions that return sum types. That's my opinion. But, maybe that's not always the best thing to do. But I don't know when it is. So sum of a list, we can reduce, get the first item in a list. Yeah, type error, no initial value. Type error can't read property 0 of undefined because we return a nothing, I guess. Huh? Why are we trying to dereference that? That sounds weird. Repeat a function n times. Oh yeah, -1 is going to overflow. Yeah, so dealing with partial functions, yeah, utilizing the option type, super good. Dangerous because they need to be treated with great caution. You might get wrong results or runtime errors. Sometimes a partial function might not return at all. Being aware of and treating all these edge cases accordingly can be tedious. Fortunately, a partial function can be converted into a pure one with guards and using the option type or the sum, maybe type. I'm not going to go over that. A total function, which returns a valid result for all inputs defined in its type. Oh, I guess it's just nice to have total functions and partial functions be functions itself. This is as opposed to partial functions, which may throw an error. Functional programming libraries and JavaScript. We don't care about that. I mean, we do, but nah, we don't. All right, and well, that's it. It's been 80 minutes and 2 gigabytes of this recording file. So I'm going to upload this to YouTube, and if it gets more than 4 views, that's going to be embarrassing.